Okay, welcome back. And again, sorry I had to be absent yesterday or Tuesday. When is the next observatory? It's next Thursday, the 22nd? All right, so let's everybody be alert for next Thursday, and I'll try to do the same. I'll try to nag you today, and next Tuesday, and next Thursday, and hopefully the weather will cooperate, and you can get yourself out to the observatory and eyeball some of our constellations, although the big telescope is not going to be. So they'll have the little, you know what? The thing I want to encourage everybody in here in the sound of my voice, the smaller telescopes that they have at the observatory, since the big one is really cool, and it is a misfortune that you can't use it. It's under repair right now, but the little ones that they're not really little, they're big nice ones, and those are amateur telescopes that an amateur astronomer might use, like everybody in this room. So if you take a notion to take up amateur astronomy, and who knows, maybe discover a comet or an asteroid, or maybe you'll be the person that discovers the asteroid that is heading for Earth to terminate us. And if you give the warning, you can be the person that saved the planet. You and Bruce Willis, of course. So anyways, those, getting used to those and seeing those telescopes, you can buy them for like a couple, $300 and on up. Some of them are really, really fancy. But there are a lot of cool discoveries, especially in the solar system, by amateurs with those very types of telescopes. So it's kind of nice. All right, we're going to talk about clicker grades, and I want you to take careful notes, and then we're going to go on and talk about planets and stuff. I just put this up yesterday. You may have noticed it, Roundup 214. And right now, we have 18 questions on the books as of last Thursday. All right? And we didn't have any on Tuesday because we didn't have lecture. Oh, and by the way, I am sorry that I did not send out or post any kind of alert on the internet. And I know some of you, came all the way in for this class and it was canceled and you didn't know you could have saved your gas and time. But next, hopefully I won't have to do it again. But if something happens, like we had to do this a lot in, last semester with hurricanes and stuff. If something happens, like I get sick again or a hurricane or whatever the reason is, I'll try and put something in web courses. I probably won't blast an email or a message through web courses to everybody simply because it's easier to just get one announcement. But I'll try to announce it a little bit ahead of time, although it was kind of a last-minute decision. Just feeling very pokey. Anyway, so while I was doing that, trying to hydrate up and rest and all that stuff, I did some of your grades. And so right now we have 18 on the books as of last Thursday. And I'm going to show you how to calculate your 25 out of 25 for your semester grade. We've got a couple examples lined up. And if you take a look at this, this one I designed to be illustrative of a foible in Canvas. And that is that if I publish a number a decimal fraction that ends in 0, it won't display the 0. And a few of you have called, have texted me through web courses saying, Dr. B, it says I only have one question. Now this student If you look at this up here, 15.1, if I upload 15.10 to indicate 10 questions answered, or 10 questions correct out of 15 answered, web courses won't display it. So if you see this, you may not, but if you do, if your thing ever comes in something 0.1, then or something 0.2 and nothing else, or any other number, just realize that's a 20 or a 10, and Canvas is suppressing it. So it really should look like this. Now, in the old days, before Canvas, when we had a different computer system called Blackboard, you could pretty much do everything you wanted, but it's either Canvas's way or the highway, so it's kind of a pain in the gluteus maximus. Anyways, let's do some examples. So as I said, this is where I want you to take notes, because what you're going to learn today is basically how to do your own grades. So you never have to ask Dr. B, what's my grade? You can do it yourself. And the only tricky part of the grade is basically the clicking percentage. So let's do an example. We got enough points on the books now, or enough questions on the books that we can do it. So the threshold, as I said, is 85% participation. All right, now so if you get 85% participation in terms of how many you answered, whether they're correct or not, you get all 25 out of 25. All right, so whatever your score is in your roundup score, you got to convert that into some pointage out of 25. Now, right now, 85% of 18 is 15.3, approximately. All right. So since you have to do, with questions, you have to use whole numbers. The break point right now then is 16 answers. And what that means is if you have 16 answers on the books, so if your thing says something 0.16, ding, or something 0.17, ding, or something 0.1 or 18.8 or 18.18, you got all your points. All right, so for instance, if Beyonce is in this class and she has 16 answers out of 18, she's answered she's answered 16 out of 18, that's 0.889 for her percentage, her participation. So go ahead and write that down. We're going to calculate with that. Actually, we don't have to calculate with that one because it's above 85%. That's 88.9%. Ding, Beyonce gets all 25 out of 25. All right, so this is the easy one. If this is you, ding, it's easy. All right. It's if you're below 85%, that's when it gets a little bit unusual. All right. So she gets 25 out of 25 on her semester grade. And as with everything Beyonce does, it all looks easy. All right. Now, we're going to talk about another person, John Q. Student. Here's a picture of him. He actually looks like a robot from space. Let's say that John Q. Student has 13 answers. So this is where the thinking begins. So write down John Q. Student, 13 answers out of 18. And students, that is below 85% participation. All right, and that means you have to use the proportion. So here's the proportion that you have to use. You might want to jot this down. It's in your syllabus as well. The procedures handout, I think I gave that out on Thursday of the first week of classes. And so the answers percentage for this particular student is 13 out of 18. So what you would do is you would put in 0.722 in the numerator on the left side of this proportion. Now, I'm going to ask you some clicker questions here in a minute. You're going to replicate this calculation. So take careful notes. All right? Now, you put that in the numerator, and then you divide by 0.85, 85%. And then when you do that, the quotient, 0.722 divided by 0.85, that works out to 0.8497. And I kept 4 decimal points on that one. All right? And so now you've got the left-hand side of this proportion expressed as one decimal fraction, 0.8497. So then what you do is you cross multiply by 25, and you clear the right side, so now it's just JQS over there, John Q. Student. And so 25 times 0.8497, that works out to 21.24, all right? And hey, you guys, I always round up. With homework, it's the same. You know, homework is just a straight percentage. Whatever your percentage is on the homework, just multiply by 15, okay, and then round up if you have to. And so this one, notice, 21.24, if you were rounding off to the closest whole number, this would round down. But since I'm a kind and generous person and try to avoid disasters, I always give you the benefit of the doubt and round up. Right? So even though this would normally, in math class, you know, those guys in the math department would say, all right, that's 21. But here, for your grade, I round it up. And it's just to give it a whole number, you know, something that's righteous. Kind of like guys that sit in the back row of class after they think I'm not looking. Where they're not supposed to be sitting. Yeah, that's right. So anyway, John Q. Student gets 22 out of 25. Now you're going to do this same calculation in a second. All right, so let me pause for questions. Get your calculators out and get your clicker out. Let's try another example and multiple choice. This one is going to be about Justin Bieber. So now this is a little bit later this semester, April 31st. 48 questions on the books, and he's got 35. All right? Question number 1. Does he automatically get 25 out of 25? Yes, no, or maybe? So calculate his performance percentage, or his participation percentage, and that'll be good. 30 seconds. This should be really easy to do. It's just one calculation. 20 seconds. And keep your calculator out and your eye clicker, because we got a bunch of. We're going to actually do the calculation here in a second. We're going to give him his points. Yeah. Your clicker just died? Oh, Lord. Let me see it. It's a dead clicker. And we can't give it CPR or anything like that. Let me see it. Let me check that out with my X-ray specs here.
Good thing it wasn't exam.
Yeah, you probably. Oh. Used. Yeah. And it's got these. All right, so what I want you to do, get some. Your toast for today, but you should be, you know, everybody's got a lecture, and that's what we're learning here. Everybody's got a lecture or two to burn, so go get some Energizers or Duracells, and just, you know. If you have a used clicker and you haven't replaced the batteries in there, you better do it, because it just flaked out on this student here, and you don't want that to happen. Okay, 5, 4, 3, 2, 1, 0. Yeah, everybody, 90% of you got that correct. Here's the calculation. If you got tripped up, here it is, 35 divided by 48. All right, that comes in at 0.729, all right, and that's less than 0.85. So as a result, we have to go to the proportion. Now you're going to do that same proportion again. All right, so if you have it in your notes, you're good. All right, now question number 2. This one's a calculation. Hit your refresh key once, and then get your calculation in. Calculate its pointage. Use that proportion that we just used a few minutes ago. It's also in the syllabus. But now using 0.729 for his participation percentage, and calculate, how many out of 25 does he actually get? All right, is it 21 or is it 19 or is it 17? Whatever it is. All right, so he's got 35 out of 48. And don't forget to round up. On this calculation, I always give you a break. All right, and I'll give you a minute. And definitely consult with your neighbor. Double check your calculation with your neighbor. See if you're, in case you're a little bit shaky, if you're a little nervous, definitely do that. So if you can do this today, then you'll be able to do it anytime in the semester, which is what I want. All right. Now you have to type in a number, so 2 numbers and then the send key. Question.
I feel like my roommate, I guess, kind of picked me over, didn't give me his clicker in the morning before he left. So
You want me to have a little chat with him?
Yeah, could you?
Me and Chuck Norris, we'll go visit him this afternoon. See if we can change his mind about that.
But are there third-party apps that could, temporarily be clickers or no?
No, not the way that we're using it. That's the Reef system. We're not using Reef. It's all right. Everybody's got 1 or 2, just like I was saying to this young lady.
Basically.
Yeah, it happens. That's why it's 85% participation instead of 100%. You get it's kind of like, you go to the store, buy one, get one free. But this one is pay 85%, get 100% of the points. So just for stuff like this, So in practical terms, it means everybody's got 1 or 2 lectures over the semester to burn. So, but now you gotta have a little chat with your roommate. Yeah. How many by the end of the semester? Boy, it's hard. I don't know. I can't tell you. I don't have a set of clicker questions set that I always think of them the day I write the lecture. So it could be 100 or more. So it just depends. I don't know the exact number, but. All right. What was the maximum?
It was about 160.
All right. 20 seconds to get your answer in. And don't forget to hit the send key. 10, 9, 8, 7, 6, 5, 4. I almost said 6, 3, 2, 1. 5, 3, 4, 3, 2, 1. I guess the flu affected my brain. All right. Now let's double check the answer. Here's your proportion. All right. So if you want to jot it down just for the. And, there's a lot of different ways to solve a proportion. I'll do a little bit different method now. All right. You can cross multiply, the 25 over to the left like this, and that gives you JB's number all by itself on the right. Okay, so you can do that. So, it's a little bit different method than the example I did in the previous slides. So, but then eventually you have to do that quotient, 0.729 divided by 0.85, and that works out to 0.8576. All right, multiply by 25, see what you come up with. And for JB, it works out to 21.44. Nice. So, Mr. Justin Bieber gets 22 out of 25 on his semester grade. And it looks like 71% of you got it. But if you didn't get it, make sure you jot this down. All right? Jot down my notes here. And it's just solving a proportion. But you have to have your participation percentage figured out. And every time that I post the roundup score for you, something, something, point, something, something, that actually encodes 2 pieces of data. It encodes in the first part, in the whole number part, how many questions you've answered, and then the decimal part encodes how many you get correct, or how many you have gotten correct. And by the way, if you want to make a side calculation, the number that you get correct at the end of the semester, if that's 75% or more, that's like half of an observatory session, 4 points bonus. All right. So there's ways for you to get bonus points, even if we don't have any more observatory sessions. You'll still be able to get an equivalent amount of dineros for your grade. All right. So we'll calculate that, or you could calculate that now. And if you feel like you want to double check with me, send me a message through the inbox system. Don't put it in discussions, because it's considered private information, your grades and stuff. So, but in inbox messaging, yeah, perfect. All right. Now, questions before we continue on this calculation. Go ahead.
So, people that came Tuesday and there was no class that know, we should get bonus points.
You want bonus points for coming to class when I don't? You know, that's a reasonable statement. However, I'm not going to do it. But I should, though. But you know why? Emotion on the floor? Yeah, I second that emotion, but I have to veto the motion simply because we didn't take attendance. You know, we could have, if Jenny had a clicker, you know, that might have been something to do. Just take attendance, you know. And a Chuck Norris question to take attendance, but we didn't do it so. But next time maybe I'll set her up to do that. All right, I'll think about it. Anything else? All right, let's keep going. Let's talk about Mercury and the other planets. All right, now, go ahead and write down the orbital specs here for Mercury's orbit. It's fairly elliptical. Now, this is a carefully drawn sketch. This red dashed line, it represents Mercury's orbit. And it's based on this table over here. Let me get my cursor. Okay, the semi-major axis is 0.39 astronomical units. The semi-minor axis is 0.38, so they're not quite the same. It's not a perfect circle. All right, the eccentricity, if you calculate it out, is about 0.206. Now, this is from the NASA planetary data sheet. Okay. Now, the column marked C. C stands for the distance of the focus from the very center. Right, and that tells you where the sun is going to be on the ellipse. If you don't care about where the sun is, if you just want to draw the ellipse, A and B are fine. But if you want to put the sun in there, C tells you, and C is a function of A and B. You know, so if you know A and B, you can calculate C. It's a bunch of square roots and stuff. You don't have to worry about that. I did it for you. But it's 0.08 astronomical units. So what that means is that the sun is 0.08 astronomical units from the center of this ellipse. Now, you can eyeball the center fairly well. And actually, you know, because the center would be the intersection of the semi-minor axis vertically and the semi-major axis, or the major axis horizontally and the minor axis vertically. And so you can see this green dot here. I always try to represent the sun with a green circle or a green dot. That is definitely, if you can see it, you look at it carefully, you'll see that it's off center. And I did it very carefully last night to make sure that it was exactly 0.08 to scale in this diagram. Now, here's another thing I want you to check. Hopefully that red dashed line representing the orbit of Mercury looks oblong to you. All right, if you don't believe me, if to you that still looks like it's a circle, here's a square. This square is 390 by 3. I made it in pixels. I made the ellipse 390 by 380. All right, and this square is 390 by 390, and you can see a little bit of daylight down here at the bottom. All right, between the ellipse and the square. All right, so it really is an ellipse with some eccentricity, noticeable even at this scale. All right, and so you know and of course the orbital distance. Here's something else you can think about. Go ahead and make a note. I'll just verbally make a note of this. Aphelion is out here to the right. So you could mark that point A. And perihelion, the closest approach, is over here to the left end of the major axis. Right? So this is like looking down at the sun and Mercury from the North Star, from the perspective of the North Star. Right? So you're looking at the major axis. And the minor axis you can kind of do yourself in your notes if you want. But perihelion, and look at the distance. Perihelion over here is really close. And aphelion over here is quite a bit farther. All right? So that means there's big variations. But it's still, no matter where you are, aphelion or perihelion, it's still really hot on the day side of the sun because you are pretty close. But did you know that they think they're, actually, do they know for a fact? I think they've had a spacecraft up there called Messenger, and they ran out of fuel, so they crash landed it into Mercury here a few years ago. But they have found ice in craters near the north and south pole of Mercury that never sees sunlight. The craters are so deep up there. You know, it took an impact up there, you know, near the north pole of Mercury or down by the south pole, and any ice that came in with the impact or any H2O and settled in the part of the crater that never sees any sunlight is still there. We think, and we know for a fact, that is true for the moon as well. And I think they found it on Mercury. So there's a big difference between perihelion and aphelion. Now for Earth, it's not huge. You know, for Mars, though, it's significant, and also for Mercury here. All right? So here's that square. All right. So you can definitely see some daylight there. All right. Now it's not a false color. It's kind of an exaggerated color image of Mercury, and this is from the Messenger spacecraft. Question.
Yeah, sorry, back to the last slide. What did B represent?
B?
Yeah.
The letter B? You mean the second column? Yeah. That's the semi-minor axis. Okay, A is semi-major, B is semi-minor, C is the focus position, and then E is the eccentricity. So, yeah, so that was a fun exercise designing this slide. Okay, so this is a color image. It's considered true color, but punched up, so it's like photoshopped a little bit to exaggerate the colors for the human eye. I want to draw your attention to this big It looks like a crater, and actually it is a crater, but it's gigantic. See that kind of roundish circle by the white arrow? That's called the Caloris Impact Basin, Caloris. And we're going to be talking about that. Here's another view. So if you want to look at pictures of the Caloris and read about it, the Caloris Impact Basin, just type in Caloris and then site nasa.gov, and you'll see tons of images and pages about it. Here's another one. Now this one is a gravity map, and it's false color, and the red indicates slightly higher density. And you know, the interesting thing about this is also it's superimposed on a photographic image where you can see the day-night term. You know, the line between day and night on any planet is called the terminator. And you can see that this is like a gibbous phase of Mercury. And so they've got the Caloris Basin, and red indicates slightly higher density of that part of Mercury. And there's another big one over here as well. This is the Caloris Impact Basin. And what they think, what they're pretty sure is the situation here for Caloris Impact Basin. It's slightly denser. They think that this is lava flows. That something like an asteroid or a comet, you know, very early in the history of the solar system, so several billion years ago, plowed right into Mercury. And who knows, that might have been enough. It's a big enough crater. It might have budged it out of its circular orbit and into a little bit more eccentric orbit. Who knows? I'm sure guys are probably trying to figure that out. But anyways, so that red in this slightly higher density, we think that's lava. Lava, big, huge lava flows. They think it's about 2 miles thick. All right? And you know what this is like? This lava flow that you're looking at, false color image? It's like the lunar Maria, the Sea of Tranquility, the Sea of Storms up there on the moon. You know the darkish areas of the moon? They call those, you know, from the ancient days, they didn't really know, you know, if it was green cheese or what. So they called those seas Maria, M-A-R, you know, like the word for marine from Latin. You know what else it's like? Lunar Maria, and also it's like some of the places here on our planet where there are enormous lava flows. Now, I think we talked about this already. There's enormous lava flows in Hawaii. There's enormous lava flows out by Yellowstone and the Columbia Plateau in the northwest United States. And there's enormous lava flows on the surface of a continent in the Indian subcontinent, the Deccan Plateau. And there's smaller lava flows, but really continental-sized ones like this, those are the three big ones in the... And then, of course, the seafloor is spreads by lava flows as well, so it's kind of cool. Now, you may think to yourself, Dr. B, how did they figure out that this was heavier? Go ahead and make a note. The reason that they figured this out, they put a really high accuracy, high precision radio transmitter on the Messenger spacecraft, and they knew that if it flew close enough to Mercury, that its radio frequency would be affected by the gravitational curvature of Mercury. Not very big effect, but if you have a highly precise radio frequency, then you can measure it. And they knew that if your frequency, you know, if their frequency was like 96.5 WDBO FM, so that's like 96.5 megahertz. So if their frequency, you know, it's transmitted at 96.5, but in the gravitational curvature of Mercury By the time it gets to Earth, it's shifted to, let's see, shorter, smaller frequency, so like 96.4 megahertz. And they can measure that. And I'm sure that the frequency that it probably wasn't FM, it was probably a lower frequency, but they measured it carefully. And so whenever they saw a lot of frequency shift, they knew that that was where the higher density stuff is, and that's why this is colored red. Here's another close-up of the Caloris Basin. And I want to point out a couple things on this one. The orangey, kind of brownish orangey area, that's the lava flows from the impact. Now, it's so long ago that it's got craters on top of that. Okay, you can see the smaller ones there. And the people that, I guess, according to Miss Jenny over here, the guys actually study the crater counts. And they could look at a picture like this and figure out a whole lot, about the whole history of Mercury. Anyway, so the orangey stuff is the original lava flow, about 2 miles thick. Now, this blue stuff in these smaller craters that came in later are craters in a crater. Crater in the lava flow that filled the crater, the Caloris impact crater. Right? So, and now here's the point. This blue stuff, they think, indicates the original surface of Mercury. And you can see a lot of blue around it, right? Around the Caloris impact basin. And there's these little craters, and they've excavated a deep enough hole, 2 miles or more, and they expose that original surface. Right? That's what they think. So here's another one up here. All right. So you look at this Caloris Basin, and all the blue areas, here's a website you can look at. All the blue areas there, they think, are the original, are places where what you see is the original base or the original surface of Mercury. So Mercury's had this big bang early in its history, and oh my goodness, it was a big one. And I'm going to ask you some questions about it on iClicker in just a second. Go ahead.
Why is it blue? Like, what is it?
It's a false color image, okay? Or actually, I think it's exaggerated color image. So this part of Mercury, it looks all gray like the moon. But apparently it's got a little bit more blue to it, and the main part of the lava in the main part is a little orangier than it still looks gray to us, but if you look at it carefully, you can say, it's got a little bit more gray. It's an orangey gray, and then the other stuff is more of a bluish gray. And so what they did is they exaggerated that, that tint, and so that we could see it, so that we can correlate it, because the detectors they have on it are really, really smart. They're a little bit better at this than our human eye. So that's why. So it's not really false color. It's kind of like photoshopped color, just so we can see. Oh, okay. This is the ancient surface. This is the impact lava. Stuff like that. Okay. Another question. Hold on. Repeat. I don't know. It's supposed to be exaggerated true color. So like I was saying, to our eye, it looks gray, but to the computer that looks at it really carefully, it's a gray that's got a little bit more blue, or a gray that's got a little bit more orange. Because gray is going to be a combination of all the colors at the same intensity. So if you do any HTML coding at all? If you know somebody that does HTML coding, every color on the internet is is encoded as 3 numbers. One to represent how much red, one to represent how much green, and one to represent how much blue. Okay? So I think white is maximum red, maximum green, maximum blue. Black is minimum red, minimum green, minimum blue. And then gray is, but all the same intensity. So if you have half intensity red, half intensity green, half intensity blue, visually it looks like just a gray, like a light gray or a medium gray or a dark gray. And so if you punch up the red a little bit and the green, it might come through a little more orangey. If you punch up the blue a little bit and leave the others the same, so instead of 50%, 50%, and 50%, perfect gray, if you go 51% on the blue, it might look like the blues, the grays that they saw in those smaller craters. So I think that's what they're doing.
And what happens is a lot of different rock compositions will have different colors. Like if you go outside and you pick up a piece of limestone, it'll be kind of a grayish tan. But if you pick up a piece of granite, it's more red. And so the similar thing is happening here where you'll have different compositions within the crater versus the surrounding area, because it will impact deep enough that it will eliminate that top layer and that top composition and dig down to the older material where there's a different composition.
Yeah, and here's the other thing, the Messenger spacecraft. Do you know what kind of gear they got on there? They probably got scanners on ultraviolet too. So this might have some ultraviolet information in it as well. But yeah, you can look at the sunlight will reflect certain colors. That's what gives everything its color. So a granite is going to have to your eye is going to look different color than a limestone or any other rock formation. And so that's also true in ultraviolet and infrared. So I'm sure they have all kinds of scanners looking all across the spectrum. But I think this one is supposed to be visual. So they're punching up the blue or the orange and stuff in this one.
Yep.
Question?
So the impact from the asteroid or whatever, the comet, that's what created the lava flows? Like they weren't natural?
The comment was the impactor, comet or asteroid, responsible for the lava flows? And the answer to that is yes. That's what they think is true. They think that's true on the moon as well. Isn't that true?
No, on the moon they found lava tubes, and so.
Oh yeah, that's right. Because the moon actually was geologically active at some point. Okay, and so.
This is geologically active on its own.
No, it's not. It's dead. It's rock. It's a rock, just like the moon. The moon is solidified. All right, now let's take a look at and think about the size of this baby. It's a pretty big impact basin, especially when you compare it to Mercury itself. All right, now what we're going to do here is go back to multiple choice. So hit the refresh key on your calculator or on your clicker, and let's do a multiple choice here. Now this one's not a survey. This one you should be able to figure out the right answer. Which of these cities is 1,500 kilometers from Orlando International as a crow flies? 2 of them you should be able to eliminate immediately. Then the other 2, maybe you'll have to make a judgment call. That is interesting.
Solid Gaussian
Hmm?
there. It's a solid Gaussian.
Yeah, for a second. Let's see, we're getting. No, option E is not good. $20 seconds.
Apparently Mercury used to have volcanic events.
Yeah, they all did.
Yeah. So some of that lava could be
Volcanic.
Yeah, usually I think if you see like an area where it's just like a spread of lava, then it's volcanic. But if it's like, you can tell usually if it's impact related, because it'll be like a huge crater, but then the lava will be around it.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Yeah, most of you got it right. Dallas. And if you don't believe me, here's an image from GPSvisualizer.com, which is a website I highly recommend if you think about maps and stuff as much as I do. I'm on it a lot of times, several times a week. This is one of the features. You can identify a location and then tell the website to draw a ring around it at any distance you like. So I did this one at 1525. Here's a close-up. Okay, so the red dot in the center represents MCO, and the red circle, the big circle, and you can see it goes all the way down to Hispaniola, down to the Yucatan, past Houston. Dallas is right on the line. Chicago up there, pretty close to Chicago. So it looks like it comes pretty close to Detroit. And it's a little bit, you know what? It looks like it goes through New York City too. But Boston's a little bit too far. All right. And now, go ahead and sketch this. Sketch an outline of the United States. Try sketching the circle and the dot at the center of Florida for MCO. The reason I want you to do that is because I'm going to show you, now this is the size of Caloris Impact Basin, right? Now, I don't think there are any impact basins that we know of on our planet that are that size, but we do know that there are some big ones. Now, the big one, the famous one, is the one down in the Yucatan, the Chicxulub crater, the impact crater that they think that impact greased the dinosaurs back in the day. Right? Now, here's the size of it. And this is why I want you to sketch. Sketch in your big circle. And this is about the size of Chicxulub. And that's a killer. You know, if we had a Chicxulub event, it would probably require Chuck Norris to prevent it. Bruce Willis, he's nice, but he's not good. But Chicxulub event would kill everybody.
Any asteroid, it's like any asteroid over like 10 pounds in, or 10 kilometers in diameter will cause severe climate changes, and then over like 40 kilometers in diameter will just wipe out everything.
Yeah, so it's, and I don't know, do you remember what the size of Chicxulub impactor was? It's a big one, but look at Caloris Impact Basin. That was a you know, the mother of all impacts, a really big one, especially considering that Mercury is much smaller than Earth. So
It was 10 to 15 kilometers.
yeah. So this Chicxulub impact here down in Yucatan, that's a bad one for our planet. We don't want any of those if we can help it. All right? But thank God, hopefully we won't get any like the Caloris impact. All right, let's do some more planetary concepts. Keep your clicker ready. We're still in multiple choice mode. Now, this is kind of an IQ test about some compounds that you may know of around the house. Ammonia. All right, multiple choice, A, B, C, D, or E. Read very carefully. And I'm monitoring. Hopefully we get almost 100% here.
I don't know. I feel like B and C are true for you.
I'm not, no, this is like an imaginary friend of mine.
You sure it's not about you at all?
Yes, I'm sure. Okay, 10 seconds to vote. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, 96% of you got it. Yeah, florists don't use it. Although farmers use ammonia, I think it's ammonium anhydrous ammonia. They use it for a fertilizer. It transfers nitrogen to the soil. And apparently someone in here actually does use it for brushing your teeth. And one person says, yes, I barbecue steaks on the grill with it. And 3 voted for florists. All right, now the reason we're bringing up ammonia is we see it a lot in the atmospheres of Jupiter and the outer planets. Yeah.
Did you use it for fertilizer also?
Yeah, it's fertilizer. It adds ammonia. Yeah, they use
D could not be right, it's not an option at all.
C or
D.
D. No, a florist wouldn't use it, but a farmer would. If I'd put farmer in there for making his, you could probably use ammonium hydroxide or whatever the compound is in your garden. But it's mostly big farmers that have huge fields that use it. It adds nitrogen to the soil, which helps plants bloom and stuff like that. All right, now here's another one. And hopefully, I'm not saying nothing. I'm not looking at anybody. I'm just going to keep my head down here. Twenty seconds to vote. Actually, this is kind of an interesting. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Ding. Yeah, sulfur. Most of you got that one right. Chuctanium. Here's the bad one. Hydrogen sulfide. Oh my goodness. Supposedly that's the one that really paralyzes your nose. And hydrogen sulfide is something that we see in the composition of the Jovian planets. So that's what we're going to talk about for the rest of lecture today. And we'll talk more about Jupiter. By the way, 2 Tuesdays from now, we have exam 2. So we'll probably be talking about, anybody listening want to know what they should study for exam 2? Solar system and up to probably asteroids and comets. So next Thursday, we'll probably be talking about asteroids and comets. And maybe even radio, or maybe even isotope, nuclear isotopes or stuff. So that, I don't know offhand what chapter that would be, but we'll talk more about that next week. All right, so a lot of hydrogen compounds. The core, we think of, something like Jupiter is pretty small. About the size of the Earth, but it's like a little nugget down there, we think. But the outer layers are mostly hydrogen, and the deepest layer is metallic or solid hydrogen, and then a layer of liquid hydrogen, and then a layer of gaseous hydrogen and some helium, we think. And that's depicted in this kind of wedge here. And down here at the bottom, you can see the Earth. They've in this diagram, they show the size of Earth compared to the size of Jupiter. And Jupiter is the biggest one. And that nugget down at the center of Jupiter, we think is about the size of Earth. All right. So there's outer cloud layers, and those are the ones where you see a lot of the, the clouds of ammonia and different compounds like that. All right. Now, here's an interesting fact. Saturn, we think, also has metallic hydrogen. All right. So it goes from gaseous to liquid to solid hydrogen, metallic hydrogen. But in Saturn, you have to go a little bit deeper because metallic hydrogen only forms at certain combinations of pressure and temperature. All right, and you have to go a little bit deeper proportionally in Saturn. Now, here's a diagram that shows that. All right, now, we don't get any of that metallic hydrogen, we think, in Uranus and Neptune, but over here in Saturn, yeah, but you have to go way down past the halfway point in the depth, in order to measure metallic hydrogen for Saturn. But now look at that. And these are kind of approximations, but this is what we think is the case. The purple area is the metallic hydrogen. That's what we're kind of concentrating on. And its metallic hydrogen is much closer proportionally to the surface. Now, Saturn's not a whole lot smaller, but it is a whole lot smaller mass. And did you know that the density of Saturn, the average density of Saturn, is less than the density of water? Yeah. So if you could have a lake of liquid water big enough, Saturn would float in that lake. So if you could find some ginormous planet, really big, with a lot of liquid water, Saturn could float like a beach ball in that lake of water. Okay, now we'll talk about Uranus and Neptune next week, but you can see, what we think about the structure of them. Now the question is, why is Saturn? It's about the same size, but the solid core is much deeper proportionally than it is for Jupiter. Why does Jupiter get to that high density, high pressure and density in temperature conditions? And Jupiter doesn't. Well, the reason is gravity, and this is a very nice analogy. If you think of a pile of pillows, adding an additional pillow to the top of the stack squishes the one at the bottom. The more you stack up, the more each one of them gets squished down, right? And so we think that Saturn doesn't have enough pillows of mass. In other words, it doesn't have enough mass. So the lower levels are squished down, but the outer layers of pillows for Saturn are not quite squished down to the density that you need for metallic hydrogen. And the opposite is true for Jupiter. Jupiter's got a lot more mass, so a lot more of the pillows, not just the first 2 or 3, but the first 10 or 15 pillows for Jupiter are smushed down to the point where they're at a density that metallic hydrogen will happen. So this is a common analogy that astronomers use to talk about the internal pressure and the difference between Saturn and Jupiter. Saturn and Jupiter, they looked at like they're nearly the same size, but they're definitely not the same densities. Okay, atmospheric pressure. Now, let's talk about atmospheric pressure on our planet. We know that if you listen to the Weather Channel, especially during hurricane season, they're going to talk in millibars. Okay, so here's Hurricane Ivan from a few years ago. The center, they'll tell you about the central pressure is 910 millibars. Okay, so 1 bar is approximately atmospheric pressure on a fair day, fair weather, at sea level. Now, if you're up in Denver, that's about a mile up in the atmosphere, a mile above sea level. Fair weather is not going to be as much atmospheric pressure. It's going to be a little bit lower than 1,013.25 millibars. All right? So, you know, and that's because there's not as much atmosphere above Denver. You know, you got a mile of really dense atmosphere between Denver and Orlando that Denver never experiences. You know, this first mile, the first 5,000 feet, is the most dense part of our atmosphere because it's further down. Okay, it's like those pillows getting squished. You know, but the further up in the atmosphere you go, and you know, these mountain climbers that go to the top of Mount Everest, you know, they have to carry. It's like going down into the deep blue sea. You know, they got to bring oxygen with them. And except a lot of them, oh my goodness, there are guys that walk to the top of Mount Everest without oxygen. But they permanently harm themselves when they do that. It's called the death zone. Once you're up above like 18,000 feet or so, 15, you know, and anybody in here have a pilot's license? Nobody here flies? Because my old advisor in grad school was a pilot, and he said that whenever you go in I think the regulation is whenever you go above 15,000 feet, you have to have oxygen, or you have to be in a pressurized cabin. So anyways, so that's Denver and Orlando and Mount Everest. Now Jupiter has a lot of atmosphere, and it gets to our atmospheric pressure way out in the atmospheric layers, way out in the cloud layers. That's because it's got so many pillows of mass, they're getting squished down real early. Okay? And so this is what we think the pressure, you know, this is the same diagram we had a few minutes ago. You know, and here it is, 1 atmospheric pressure, 1 bar, so that's about 1,000 millibars. That's way out here in the cloud layers. And it rapidly gets really, really, really high pressure. All right? And if you know anything about Clark Kent and Superman, Superman can take a piece of coal and turn it into a diamond because of the pressure. You know, something that only Superman knows how to do. Okay, but actually, we know how to do it now. They've figured out how to make synthetic diamonds by putting them under pressure and certain temperature conditions, and you get carbon converting, you know, just graphite or something converting over to a diamond. It's not a real hot gemstone, but it is a useful diamond. Diamonds are useful for other things. Anyway, so we got a lot of pressure. Now, hydrogen liquefies in the Jovian atmosphere at about 2,000 Kelvin. There is another Kelvin temperature, and I told you before, yeah, we're going to be talking Kelvins the rest of the semester. 500,000 bars, so if you go to the bottom of the Marianas Trench, you're not at this pressure. You know, the oceans of Earth are a smidgen of water compared to the size of the Earth. It's not even a puddle. It's like a grease slick. It's a smear of water. Now the cloud layers on Jupiter, the reddish-brown stuff, ammonium hydrosulfide, NH4SH. And, you know, when you look at pictures of Jupiter, you'll see like the Great Red Spot. You know, that big storm. We think that it's red is from ammonium hydrosulfide. Now, the whitish layers that you see, you know, we see these smaller white spots, you know, flocking around in the weather bands on Jupiter and Saturn too. Ammonia and water. So ammonia is a little bit higher up. Ammonia a little bit, or water a little bit lower down. And, you know, there's other kind of clouds and stuff that, you know, the Voyager and Cassini and all the different orbiters and probes. The Cassini, no, it wasn't Cassini. What was it that dropped that probe into Jupiter's atmosphere. I think it's the Galileo spacecraft dropped a probe into the atmosphere of Jupiter. So we know, all kind of, but this is the headlines, different colors and stuff. It's kind of cool. Okay, and ammonium hydrosulfide, I'm looking here at my notes. Ammonium hydrosulfide is smelly. It's got that sulfur in there. So if you were to smell it, open up the hatch of your spacecraft, let a little bit in, you'd be going, please. Now let's talk about the Jovian moons. And oh my goodness, there is a lot of cool stuff happening in the Jovian moons. Now, Galileo, I'll give you a little historical footnote to history. Galileo Galilei is the first astronomer that used a telescope. And one of the first remarkable discoveries he made was the 4 big moons of Jupiter. They're called the Galilean moons. Io, Callisto, Europa, and Ganymede. I think that's the names of the 4. Okay, and those are the 4 that he could see. Now we've seen a whole bunch more. All right, since then, because we've got bigger telescopes, sharper, better definition and stuff. Now here's one, Enceladus, Enceladus. This is an image. It's not a black hole. It's just that the Cassini spacecraft was between Enceladus and the source of light. So it's that black circle. Enceladus is one of the smaller moons of Saturn, but it's kind of a cool moon. So, and what you're looking at here you're actually looking at the rings of Saturn. And this little blob down here, see that? That's another moon. That is, what's the name of that one? It ends in O. I want to say Fargo, but that's a city in North Dakota. Anyways, that's a little moon there, one of the other moons. There's a ton of moons. Notice anything else about this image? What do you see? Yeah, look at this stuff down here. Look at this. My friends, those are geysers, water. A lot of interesting stuff. All right, right now the count is 170, I think, last time I checked. That's for all the Jovian planets. Jupiter 67, Saturn 62. Some of them are big, like the Galilean moons. Some of them are a little bit smaller, and some of them are really small. Uranus, has 27, Neptune 14. And we think that most of them formed when in the cold outer solar system. So down in close where Mercury was, everything is really HOT. And so you don't see a lot of volatile chemicals down there. They get evaporated away and pushed out to the outer part of the solar system, where they can then refreeze and resolidify into a moon or a comet. And so that's what we think is true about the moons out here. So they have a lot of ice. So when an astronomer says ice, he's thinking water ice, he's thinking CO2 ice, carbon dioxide ice, ammonia ice, methane ice, stuff like that. All right, it's 14 after. Let's dismiss. I'll talk about the moons of Jupiter and Saturn on Tuesday. So start reading about the outer Jovian moons. You're dismissed. I'll see you next Tuesday.